Howdy everybody, welcome to module number 14, and we're going to learn about simple linear regression in this video. And I'm really excited because this is like right at the end of the course, and it's a lot of material to try to synthesize in one semester. And here's what simple linear regression looks like, and that might also look like I'm trying to create flying vehicles with zero thrust propulsion, which looks like I'm trying to create a rocket spaceship or something with this stuff here. But it kind of could look complicated, but actually this simplifies everything. And so we're just going to start off here and we're going to look at it. And the entire thing with simple linear regression, like my favorite area to focus upon is right here. It's linear. It's a line. And if you remember, like back in, I don't know, what was it, algebra? We had y equals mx plus b, and that's like the point slope intercept. That's the slope intercept form of an equation for a straight line. It's y equals mx plus b. And so if you understand that, and if you remember that, like, I'm not sure when that's taught, like algebra, maybe, it's been a while. I think that might be algebra. But if you remember that y equals mx plus b slope intercept, right, form of an equation for a straight line, that's what we have here. We have a straight line, and that straight line is using the y equals mx plus b. And you can see that over here, it's y equals mx plus b, but here they have y equals b1x plus b0, and then they also wrote it y equals b0 plus b1x. But this is the same mathematical thing as y equals mx plus b. And what is that y equals mx plus b? That is the regression, right? And what is regression? What's happening with regression? So we have these different dots here. And so let's say this is a pizza parlor. And it's actually a pizza parlor company. And they make pizzas, and they have different pizza parlors in different towns. And these are the different towns where they have the pizza parlors. And they put all their pizza parlors right next to college campuses. Okay? And so here is the number of students that go to the college where they put the pizza parlors near. So at this college here, whatever that is, these are in thousands. It's student population in thousands. So here there's like 2,000 students. And in these, there's like 6, and these are like 8, 7,800, 8,000, something like that. Here's like 12,000 or 11,000 maybe, 10,500. Here's like 10, 12, 14. This is like 16, 15 or 16. Here's like 18,000, right? And so that's how many students. And then here are the quarter sales. And so at this college where they have 2,000 students, they do $60,000 in sales every quarter. And at this college where they have 8,000 students, they do like $85,000 in sales every quarter. And so you could see that there is a positive relationship between the number of students who go to the college and the quarterly sales that the pizza parlor realizes. And that linear relationship is like estimated by this line. And this line is, like if we were just to look at these dots, and we asked ourselves, where would we put a linear line such that that linear line passing kind of, through all of those dots, that linear line passing through all those dots, we're minimizing the distance between each dot and the linear line, okay? We're minimizing the distance between each dot and the linear line. And so we're going to find what that dot is, and we're going to subtract that from, some value on the line, and then we're going to square that, and just to make sure it's positive, and in doing that, we're going to find that least value. We're going to minimize that. And that's regression. That's how you come up with this. And so these different parts here, when I said, hey, we're going to go to some point, so this point here, we'll call that yi. So it's, here's your x-axis, and here's your y-axis. And by the way, you see on the x-axis down here, it says this is the independent variable. X is the independent variable, and it goes on the x-axis. And so the independent variable is like, right, it's like how many students go to that college. And then, in the dependent variable, it goes on the y-axis, and it's y. And the dependent variable is how much sales, I don't know how to say that, I can't talk, it's the end of the day. How many sales does the pizza parlor realize each quarter, and is that connected to the size of the student population at the college that one pizza parlor is near, right? So the sales here is the dependent variable, and what we find, and that's what we're looking to see. We're looking to see if the independent variable, x, influences the dependent variables, y. Do the number of students at the college that is near the pizza parlor, at the college that is near the pizza parlor, does the number of students impact the number of quarterly sales? So students are the independent variable represented by x, and quarterly sales, the sales, are the dependent variable end of the day, and it does it depend on the number of students, and it does, right? That's what we're looking to see. And so here we have y, and y is the dependent variable, and we have this y here, which is some sales amount, right? That would be like 115, and we take that yi, and I is one of the points, and so we take that yi and we subtract from it y hat. I'm going to call that y hat. I actually don't know what the name is. I'm going to find out. Hold on, let me see if I can find out. Okay, so I've uploaded this to ChatGPT, and so here's estimated simple linear regression equation. There you can see the y hat. And I'm asking ChatGPT, in this equation, is the y hat variable called y hat? And I'll just make that all lowercase so it doesn't think I'm trying to ask about case. Let's see what it says. The suspense, and ChatGPT's maybe at the end of the day. Yeah, y variable in this equation is often called y hat. In the context of regression, y hat, pronounced y hat, represents the predicted value of the dependent variable y based on the regression model. It is an estimate derived from the linear regression equation y equals b0 plus b1x. And why they didn't do that y equals bx plus b, I don't know, because that's what we're familiar with from algebra. Again, I think statistics doesn't do a very good job of making things simple and clear to understand. Anyhow, so you have y hat. So you have each data point minus y hat, which is, and over here we had an explanation of y hat, which y hat represents the predicted value of the dependent variable y. The predicted value of the dependent variable y based on the regression model. So this line represents the predicted value of the dependent variable y based on the regression model, okay? So that's y hat is equal to that line, mx plus b, b1x plus b0. All right, so we get this line here, and then this is called right here, this process, that little calculation is called the ith residual, that part right there. And the difference between the observed yi and the predicted y hat. And it measures how much observations cluster around the y hat line, right? So this is measuring how much observations cluster around the y hat line. And so this is also called the sum of squares due to error, right? And it's that little distance right there. So it's from the dot to that regression line. From the dot to that regression line would be the sum of squares due to error. And then we have a couple of other measures here. So if we were to take the mean of all of these values, so 60,000, 80,000, 100,000, 110,000, 108,000, whatever those are, and then these values here, 138,000, whatever it is, 142,000, 145,000, 150, 160,000, 180,000. If we were to find the mean of all those values, it would be whatever they are, right? And those values, this is the example from the textbook, and those values can be determined. We have an entire table, right, with all of the data right there. And so that mean would be like at 130 or something like that. So the distance between this regression line and the mean, right, for each point is called the sum of squares due to regression. And it's y hat, which is that line, minus y mean, the mean of all the y values. Y, dependent variable, right here, right? Y is right there, dependent variable. So this is the difference between the regression line and the mean. This is the difference between the point and the regression line. And then both of these, if you add them up, both of these. And here you could see that right here. SSR, which is this one here, sum of squares due to regression, which is like difference between here and there. And then here we have sum of squares due to error, which is the difference between the dot and the line. If you add both those up, SSR plus SSE, SSR, SSE, both of these lines right here, if you add them up, the distances, right, it's going to be this amount. It's going to be from the dot to here. So if you go from the dot to the line, and then from the regression line to the mean, right, that's going to be the same distance as if you go from the dot to the mean. Same distance. And that's what this says. Okay, this equation right here. So just to look at the other little scratch terminology here, you have the total sum of squares right here, and it measures how much observations cluster around the y mean, right? The y mean right here line. So that's what sum of squares, total sum of squares, that's what that's measuring. How much these observations cluster around the mean. It's the distance from the observation to the mean. You can see that right here, from the observation, that point right there, to the mean, it's that distance. So that's measuring how much these observations cluster around this mean. And then this is like how much these observations cluster around the regression line. And the regression line is determined by finding the least amount, right? And there's some calculus involved in that. And we're not doing the calculus. And then, you'll see that in a second here. And then also we have this last one here, which is the distance from the regression line to the mean, and that's the sum of squares due to regression. So we have a couple of different formulas here, and we also have a coefficient of determination and sample correlation coefficient formula. And this is like the regression model, and so this is kind of the model, and it also adds to it some error. And these uppercase B's, or these funny looking B's, those funny looking B's are for the population. And then we have the regression equation. So, the model says, hey, there could be some error. And then the equation is like, here's this, y equals mx plus b formula for a line. And then we have here's the expected value, this EY. And it's also the mean, okay? So the expected value, the mean of all of these points, which is a little bit confusing because it's a different mean than this mean right here. But they refer to it as the expected value most of the time, but they also say it's also the mean. So it's the mean, I guess, if you were to look at like between all of these points in this way, like through regression, maybe it's the regression mean. I don't know what they mean by that. And then we have it's okay. And we have the estimated regression equation. And so we have y hat, which is the predicted value, or also known as the point estimator of the population expected value. And we have y hat there. And then we have small b's. And the small b's are for the sample. Okay, so it's not the population, but we're going to estimate what's going on with the population with our sample. And that's what the small b's are. So those are like 3 different formulas just to kind of get to this formula right here. And just to emphasize that we are doing this with a sample to make inferences and estimations about the population. And if you really think about the entire model, there could be some error in there. And further into the chapter, right, we may or may not cover this in this course because all we have to do in this course is teach simple linear regression. But further into the chapter, if we decide to go a little bit further and go beyond what is required for us to do in the class, there is testing for significance, and you could test to see, like what does that error look like? And with what level of confidence could I say that this is a true estimation of what is actually occurring in the population? My sample's an estimation of what's occurring in the population. And so that's my little way of kind of explaining regression. And this probably isn't completely clear to you yet. But as we go through these slides here, we've got like, 28 slides to go through. As we go through the slides, we'll come back to this. And having this little chart right here is going to be super helpful. Like knowing that the dependent variable, it goes on the y-axis and it's represented by y, hugely important, right? You can see here that all these things have y in them. And then knowing that y hat, and notice here's y hat, is the sample estimation, right, of the expected value for y, and that we have the little b's, and that's for the sample, and the big B's are for the population. Just knowing those and knowing that the independent variable x is down here on the x-axis and that this is a dependent and this is the independent variable. And then understanding, this is hugely important, understanding the relationship between SST, SSR, and SSE, and just visually being able to see it here. Like it's the distance from a point to the regression line. That's SSE. And it's represented by yi minus y hat. The line is y hat. A point is yi, where I is whatever, like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? We got 10 things, so it could be y1, y2, like maybe this would be y3, this would be y4, this would be y5, whatever, y6, and this would be, the y value would be like 138 maybe, and 138,000. And so that yi would be 138, and then we'd have the expected value, that y hat for that point, and that x for that x, and then we do our little calculation. What's the difference between them? We'd find the distance from that point to the line, and that's known as the sum of squares due to error. Like understanding that's the SSE, this is the SSR, here's y hat, this point, minus y mean, that point, and that's known as the sum of squares due to regression. And if you add both those up, you get the sum of squares total, and that's the whole distance from the point to the mean. Like knowing this stuff right here is really going to help you as we go through the rest of this stuff here. So I'm going to leave that as a little introduction to regression, and in the next video we're going to start going through the PowerPoint presentations. It's the end of the day. All right, see you in the next video.